Section 12, Matter and Energy Classification. So far, I have held off specifying exactly what is matter and what is radiation in these equations. For cosmology and the Friedmann equation, matter always means the total energy, including rest mass energy, of non-relativistic matter, particles with non-zero rest mass that are not traveling the vast reaches of the universe at near the speed of light. And since this is non-relativistic, the kinetic energy is negligible compared to the rest mass energy, so the kinetic energy and pressure never appear. All ordinary matter that we see on Earth, protons, electrons, neutrons, counts as matter here, with one exception we will get to in a minute. If you know that cosmic rays travel the universe at near the speed of light, the amount of cosmic rays is negligible to cosmology. The cold dark matter, CDM, in and surrounding galaxies counts as matter here and actually is 5 times higher energy density than ordinary matter in the universe. The adjective cold means non-relativistic when the universe was tens of years old and radiation dominated expansion. Dark means rarely if ever interacting with light or with ordinary matter. Scientists do not know what dark matter consists of, when it was created, or if it has ever interacted with light, ordinary matter, or itself, other than through gravity. Most of the mass of each galaxy is cold dark matter. 84% of the universe's non-relativistic matter is cold dark matter in and surrounding galaxies. 16% of the universe's non-relativistic matter is ordinary matter, protons, neutrons, electrons. This is 5% of the energy of the universe. Cosmologists call this baryonic matter. To particle physicists, protons and neutrons are baryons, but electrons are not. But the energy of the electrons is insignificant to cosmologists for most of the history of the universe. The ordinary baryonic matter is about 13 hydrogen ions to every helium ion or atom, about 1 hydrogen ion every 5 cubic meters, and 1 helium atom every 67 cubic meters, on average across the universe. This is less than 10 to the minus 30th of the density of water. The ordinary baryonic matter density has been less than the density of water since the first second after the Big Bang. In a later video, we will see how the helium came about, also a small amount of deuterium and lithium. To recap, presently, 69% of the energy of the universe is dark energy, whose dark energy density, not total energy, is constant, or nearly so, independent of expansion. Very different from matter and radiation. This is some kind of energy density of empty space. This is a mystery. Almost all the rest of the energy is non-relativistic matter, rest mass energy. 26% of the energy of the universe is dark matter, within galaxies, surrounding galaxies, and between galaxies. Dark matter is detectable by its gravity, but it does not clump together, and its substance is a mystery. 5% of the energy of the universe is ordinary matter, rest mass energy. Half of this amount has been detected as stars, gas, galaxies, and intergalactic gas, but half of the ordinary matter appears to be missing. This is a mystery. Lots of mysteries in the standard cosmological model. All electromagnetic radiation, from gamma rays to visible light to radio waves, travels at the speed of light in vacuum and counts as radiation to cosmology and is subject to cosmological redshift of wavelength and photon energy due to expansion of the universe. There are about 400 million cosmic microwave background (CMB) photons per cubic meter, much more than photons from starlight, which gives about 1/10 the energy density of the CMB presently and less in the past. There are about 1.6 billion CMB photons for every nucleon, protons plus neutrons, in the universe. This high ratio is related to the disappearance of all antimatter antiprotons and antineutrons in the first second after the Big Bang. Particles called neutrinos also traveled near the speed of light in the first millions of years of the universe and count as radiation in cosmology. Neutrinos are ordinary matter particles with no electrical charge, but their rest mass is so small, less than 1/millionth of the electron mass, that they traveled near the speed of light in the early universe. Neutrinos have been traveling the universe since the first fraction of a second and account for 40% of the early radiation energy density, whereas present cosmic microwave background photons had been 60% of the early radiation energy density. Because neutrinos do not emit or absorb electromagnetic radiation, some areas of astrophysics count neutrinos as dark matter, but cosmologists do not. When I say neutrinos, I always mean neutrinos and antineutrinos. They were unable to annihilate after the first 100th of a second. Neutrinos have had minimal impact on the evolution of the universe after the first 100th of a second, so feel free to ignore them, though I will include them for completeness. Neutrinos from the early universe might no longer be relativistic, but they are typically still accounted as radiation, because they were relativistic when radiation dominated the expansion of the universe. There are presumed to be about 340 million cosmic relic neutrinos and antineutrinos total per cubic meter in the cosmic neutrino background. Astronomers have not yet detected this background, but would like to confirm understanding of the first second after the Big Bang. If you know about gravitational waves, I have never seen them counted into radiation in cosmology. Expansion of a perfectly uniform energy density would not produce gravitational waves, but density variations might. Astronomers have not yet detected primordial gravitational waves, but would like to.